So we previously looked at the construction of data from some objects on a map, and then we defined the position of each object as nodes, which were then given to different objects. So our towns picked up the positional information from our node table, and similarly the lines. We defined a line as consisting of certain nodes, and the locations of those nodes were picked up from a table. So this is data stored in a database. We have several different types of database that we can use. There are most commonly we use the relational database. There are others are also used, but there are four types. We have the relational database, we have the entity relational database, the object-based database, and the semi-structured. All of these do exist, but most commonly, for example, the shapefile uses a relational database. And what is a relational database? It is basically this thing that we looked at before, what I've spoken about, with the relationship being go to this table and pick up that information. There's a relationship between the data here and the data here. So these arrows are essentially the relationships between the different tables. You can find this relevant information by going to this table here using so-called keys. So we have these keys here. This is our key. We define it as being the key by saying if you take this information and look in this column, you will find, using the key here, you will find the relevant information. So these are the keys that connect the data in a relational database. The entity relational database, very similar, but we have a very strict definition of what can exist in it. Object-based, we'll basically skip over, but you've got data and some methods associated with it for accessing and working with that data. That's for programmers. If you're familiar with object-oriented programming, it's kind of similar there. And then we have the semi-structured, the other perhaps more important type of data. And so the semi-structured database it's XML in many cases, which we then get different flavors of, such as GML, which also then has a sub-flavor, as it were, subset called KML, which you should have used already, which is the keyhole markup language, Google Earth, Google Maps data stored in the KML format, KMZ if it's zipped. So this is a set of predefined, in many cases, predefined ways of describing data, but so we have a scheme that says you may have, any object has to have at least these qualities, and then there's a suite of other qualities that they may possess. And then within that, there exists a subset, an open subset that isn't defined, where you can define your own types, attributes of data that can exist within there. It's a very flexible system. The structure of it, obviously we have these well-defined keys, or these well-defined terms that say this is what this type of data is, but it doesn't exist in a particular order necessarily. We have to open and close the structure. We have to know what belongs to what, but it requires a lot of analysis to find for the computer, to find the relevant piece of information. We have to have a very logical structure in order to find our way down, whereas the relational database was very straightforward, laid out for us. Go here, look there, go there, look there. The semi-structured one requires a bit more thinking on the computer's part, as it were. It's a very rich format and very flexible, but requiring more of the computer and us when we try and read it. So normally we're talking, when we're looking at databases, we want to represent our attribute data in a simple format that we can look at and understand, and also that the computer can easily access and reference. And this is done, this is exemplified best using the relational model in, for example, a shapefile or a geodatabase, where we have an attribute table. So we have various attributes here. The attributes are represented by these different columns. So these are very peculiar names coming from data from the Swedish Land Survey, Lantmäteriet. So that we have different types of possible attribute that can exist. Here we can say that many of these objects do not have these attributes. They're left completely empty, but they potentially could have those attributes. Here these attributes are filled for each of these objects. So each row here represents one object. Not necessarily one polygon, but one object, or one line, or one collection of lines that is an object. So each row is an object. We can select that, mark it out as an object, as a thing, and it will be represented on our map as well as being one object. So the table contains the information about a particular object's qualities. What we do not see in this table, generally speaking in GIS, is the geometric description of that object. That is stored somewhere outside of this attribute table. This is purely the non-geometric attributes of this object in this table. This is fairly standard in a lot of GIS, relational databases for GIS. Whereas in say an XML format, everything is stored together in one long collection of text. So how do we get information from these attribute tables, from these relational databases? The standard is something called structured query language, or SQL. And we set these queries, questions essentially, logical questions or statements to the database to get out information, or to put, actually SQL is capable of performing actions on the table, changing the table, editing it. In GIS, we use a very limited subset of the tools available via SQL. But so we'll look at the basics of SQL relevant to GIS, not the full suite of SQL functionality. This is a GIS course, not a database course. So we're not going to be looking at the more advanced functions in database management, just simple queries to get out information. And the reason we can do this is that a lot of the database management is constrained by what we expect from GIS data, but also because the program, the GIS software, will be doing a lot of the heavy work for us, so that we don't have to do too much thinking, because our brains are busy thinking about other more important things. They should be. But we need to know a little bit about SQL. So let's start by going back to some basic logic, some fundamental stuff. We've seen this before, hopefully, but let's just go over it again because it is quite important. This is how we should think about our data. This is relevant both to SQL and to other mathematical tools that we will use within GIS, raster and vector. So we have, we're going to perform analyses. We have two things. We have perhaps two balloons, we have two objects that can be either blue or red. So we have object 1 and object 2, or we have one object, is it blue and or red, we can see here, but we have these two qualities that we're investigating, the blueness and the redness of a situation. So in this first situation, whatever it is we're investigating has no blueness and it has no redness. The child has neither a blue balloon or a red balloon, or the car park has no blue cars or no red cars, or whatever the situation is that we're looking at. It's 0, 0. And if in this AND column here, we're looking at this, and the AND says, are both conditions true? Do we have a blue balloon and a red balloon? Well, no, we have neither, so we can't have both. And in the OR column, is one of the balloons, do we have either a blue or a red? I don't care which, but as long as we have one of them, although we don't have either of them, so that's not true. And then there's this slightly more complicated one, this XOR here, exclusive OR. It says, is one and only one of them correct, true? Do we have a blue or do we have a red? but not both at the same time. Well, no, neither of them's true, so that's not true either. We go on to the next situation here, and we have a blue balloon, or there is a blue car parked in the car park, or the situation that you're thinking of. And in the AND column, are both of these conditions true? Do we have a blue and a red? Well, no, we don't. We just have the blue. We go to the OR column. Do we have a blue or a red? I don't care which. Yes, we have a blue. We just said so. And then the exclusive OR. Do we have a blue and only a blue, or do we have a red and only a red? We have blue and only blue. The red is not true. We don't have a blue. Good. Then the exclusive OR is happy, because there is blue and only blue. Similarly, on the next row, now it's reversed. We have red, so we don't have both, so AND isn't happy. The OR is happy because we have blue or red, and it happens to be red in this situation. And the XOR is happy because we only have one of them. We only have red in this case, but it's because we only have the one, not both are true, it's happy. Then we go down to this last situation, and we've got a very happy child there. They've got two balloons. We've got a blue and a red balloon. Yay! And so they've got the blue and the red. So AND is fulfilled. Yes, we've got both red and blue. The OR's happy either way. Do I have a blue balloon? Yeah, okay, done. We don't need to continue the analysis any further. We're done. But it could go to the red and look at it and say, yeah, actually, yeah, we're good there as well. XOR, little picky, says, do we have a blue balloon? Yeah, we do. Oh, I'm sort of happy. And then it looks here and says, oh, we've got a red as well. And, it's a grump. Doesn't want too much happiness. So because the child has two balloons, one blue and one red, it's not happy. So it's 0. And we can continue with this type of analysis using larger sets. Set theory comes in here, and we can query which numbers exist in both A and B. So we can see here that number 1 here, this integer, does not exist in B, so we'll get rid of that. But 2 does. 3 doesn't exist in B, but 4 does. And then obviously 6 and 8 do not exist in A. So our combined A and B becomes the subset 2 and 4. And similarly for all of these others. And then the not here, what is in A but not in B? We're looking at those numbers that exist here but don't exist in that set. So that's our not.